We're just about ready to go. Sorry we're late getting started, but I had a bunch of papers to return to people. But before I get going, let me say this. I don't think this will bother anybody tomorrow because I seldom see any of you on Tuesday or Thursday, but I do have a doctor's appointment tomorrow morning at 8:20, and that means I have to be at the labs at 7:20, meaning I won't be on campus until probably getting pretty close to 10 o'clock, because the doctor's appointment, if it's 8:20, hopefully I'll be through 9:45 or 10, and then back to campus between 8:20, then I'll hopefully be through 8:40 to 9, be back on campus 9:30 to, or 8:45 to 9, be back on campus sometime between 9:30 and 10 o'clock. I've already made up that class, so nothing there. So my office hours will start when I get back on campus, right around 10 o'clock, maybe a little later, depending on how long the appointment and how far behind he's gotten or whatever. So there's that little mess up there, hiccup in my schedule there. Other than that, everything's pretty good until next week. I believe it's Tuesday of next week. I have what they call a planning hearing over on the Birmingham campus at 10, I believe it is. I'll check on the times on that. And that means my office hours will be shot that day pretty much from 10 to 12. The meeting goes from 10 to 11. I think I have to stay a little bit for the next meeting because I have a follow-up with another department. We do some things together on that. And then I'll be coming over here and probably just have time to eat lunch and start my 12 o'clock class. So there's that. And let's see. Allison? No. Yeah. Monique, right? You said, okay, I couldn't hear, but I thought it was you. Okay. Okay, now, when we go to the lab or sometime else, remind me to give both of you your first two tests, because the last person that turned in, I've been waiting. She had a medical emergency come up, and so she's been behind, but she kept contacting me saying she was going to do it. She finally turned in a whole bunch of stuff on Thursday, so I'll can return the first two tests to you. She hasn't returned any labs yet, so I can't do that. So we'll go from there. All right, so that's coming up next week. So my office hours will be messed up, I think, next Tuesday, at least in the morning. The afternoon should be fine. Okay. Now, what we're doing in this class, oh, and by the way, we only have basically about 2 more weeks left of classes, and then we have finals. So please get your stuff in. Yes.
So the final is going to be like, we take it in here, right?
What's that?
Final, we take it in here?
No, actually, more than likely, the final will be the last chapter test, unless we finish, and then there'll be a comprehensive, but it'll still be a take. Okay. Essence just came in. And remind me either during lab time or sometime to get you your first 2 tests back, because the last person to turn them in finally got several things turned in last week, so I can return those to you. So what we're going to do today is continue in topic 9. We'll go right up until about 3:30, and then you'll have the lab from 3:30 to 5:30. Okay. And I don't think it'll take that long. The lab itself part, there are some questions to answer at the beginning or anytime you want to, and then the lab won't take so awfully long. This is the lab back from topic 6, the momentum topic. But we got started last time in solids, fluids and solids, topic 9. Any questions before we get going on that? And several people who were here earlier did not get test 6. So if you didn't get test 6, get that when we go to lab 2. It'll be our 6th lab, and I gave the 6th test on last time as well. All right, any questions? Topic first 6 topics or what we've done so far in 9. Okay, I believe okay. Did we go over this slide? I indicated in my thing here we did, but I can't remember for sure if we did. Did we do this slide last time? Let's go over it quickly if we did. Solids, as we said before, have a definite volume. That's because of the crystal structure is fixed. Not only are molecules in certain proximity to each other, they are fixed in place relative to each other. That gives a solid a definite volume. Okay, the placement, sorry, I said it backwards. Proximity to each other give themselves a definite volume. The fact that they also are fixed in the crystal lattice, that gives them a definite shape. Molecules are held in those specific locations by the electrical forces, and let me just briefly tell you what they are. You have several types of bonding, and all of it has to do with electrical forces. You have ionic bonding by one atom losing an electron or gaining an electron. The other one does the opposite, gains or loses, and then this one would be if, say, this one lost an electron, it becomes a positive ion. If this one gains an electron, it becomes a negative ion. So now they're attracted to each other electrostatically, and that's a very strong bond. Okay. Also, another way that electrical forces hold them together, they can share electrons. Say, if this is one that shares an electron with this one and with that one, then those are in place, and then these two. So you could be sharing electrons. That's also electrical forces. And then there's some others. Perhaps those are the main. We call them electrostatic or ionic bonding and covalent bonding. They vibrate around the equilibrium positions. Okay. Now this is a model, and I'll jump to this one. This is a model of, say, a sodium chloride atom. Just happen to know because this looks like a cube, and those are cubic crystals. This would be a sodium chloride, sodium chloride, sodium chloride, sodium chloride. Okay. Every other one is a sodium and a chloride, but no two sodiums attached to each other. This is a sodium, that's a chloride, that's a chloride, that's a chloride. This would be a sodium, and a sodium. Okay. They cannot have two dissimilar ones adjacent to each other. Now, the only motion this is allowed is a vibrational motion, and that's why they model them as springs. They're really not springs, okay? They are flexible bonds, but they can vibrate or give and take just a little bit. One of the ramifications of this, most solids, when you heat them, they expand. When they cool them, they contract. Notice I said most solids. Sorry, thank you. Y'all will wake up. Okay, good. But that's what makes a solid a solid. They are fixed positionally and they're fixed proximally to each other. Okay? Proximity gives them the definite volume, the position gives them their definite shape. Okay. All right. External forces can be applied to the solid and compress the material ever so slightly. Okay? External forces can be applied to the solid and compress the material. In this model, the springs would be compressed in that last model that we showed. Now, if that compression went along with a lot of heat and over a long period of time, you may actually change the crystal structure from one to another. Can anyone think of any material that changes its crystal structure under heat and pressure? Diamond, exactly. Carbon at normal temperatures and pressure is a black, sooty, sort of slick, almost solid. Two-dimensional structure, you might say, slides past each other. We often call that graphite. Graphite's a fairly slick material, and sometimes it's actually used as a lubricant. If that graphite undergoes an enormous amounts of heat and pressure over a long period of time, it actually adjusts and it changes its crystal structure, and that two-dimensional graphite, which is slick, becomes a three-dimensional diamond, which is abrasive. In fact, the strongest bonding of just about any that you find is the hardest naturally occurring substance known. Okay? So you go from being, and it's exactly the same chemical structure, it's just that the physical structure is different. So external forces can be applied to the solid and compressed material. The springs will be compressed. When the force is removed, if that's all you were doing was pushing them in other words, making them compress, then when the pressure of the force is removed, the solid returns to its original shape and size. That property is called elasticity, okay? And that's when it doesn't change its actual structure. So I was giving an example beyond what they were meaning here. Just you're compressing it and then it comes back. Elasticity is not that it's stretchable, it's that it returns to its original shape. That's what we mean by elasticity. And that's really what you want elastic to do. Not the fact that it stretches in the first place, but the fact that it returns to its original shape. Okay. Here's the crystal solid we were talking about, another picture of it, this time without the springs in there. The atoms have an ordered structure, and this is the very one that I was talking about before. This example is salt. The gray being the sodium ions, little bitty sodium ions, the green being the larger chloride ions. Now, why would the sodium ions be smaller than the chloride ions? What is it that makes up most of the volume of an atom? The electron flying around like crazy. The protons and the neutrons, which is most of the mass of the atom, in fact, the vast majority of the mass of the atom, in fact, 99 and a fraction percent of the mass is all in that tiny little nucleus. The volume, though, is occupied by that electron cloud. It's just all around it with almost no volume, no mass at all. So when it becomes a positive ion, that means it's lost an electron. That means it's not electrically neutral anymore, so that proton-rich nucleus is pulling the electrons tighter, closer in, because it's a net positive charge. So actually the electron cloud shrinks somewhat for the sodium. On the other hand, the chloride ion, because it's gained an electron, now it's more. It wants to get further from the nucleus because the nucleus is a positive charge and it's a negative charge, the electron cloud is, so it actually expands. So sodium chlorides, okay? And you'll notice that no sodium attaches to anything but a chlorine, no chlorine attaches to anything except the sodium, okay? So that's the deal with this one simple solid, sodium chloride, commonly known as table salt, okay? And if you happen to have a really good magnifying glass or a telescope, look at some salt crystals sometime. You'll see they make these perfect little cubes, or pretty close to perfect little cubes. Now, you have other solids that don't form up their crystal structure well. In fact, hardly at all. The atoms are arranged almost randomly. Again, usually a positive ion will only be attached to a negative, and negatives only to positives, but they don't form a three-dimensional or even a two-dimensional crystal. And that usually is because the crystal formation happened too quickly. In fact, it didn't happen. The object cooled so quickly it did not form an original crystal structure. structure. We often call that glass. Now, we call it glass if it's in the windows. Has anyone ever watched a glass blower do his work? How does that work?
I've seen them like this, use like a torch and stuff to do it.
Okay. They heat them up. They have basically sand. Okay, that's silica, and those are little crystals, little bitty crystals there. They heat it up very, very, very hot, and it melts them. Okay, and then they do whatever they're going to do to the glass, blow it, spread it, you know, whatever they're going to do, and then they let it cool really quickly, like immerse it under water or something like that, and it cools so quickly that they do not form back into a crystal structure like they had when they were the little sand particles. They are now amorphous, and they don't quite crystallize like they should have or would have before. Okay, that's called an amorphous solid. Doesn't follow a definite crystal pattern. And glass doesn't just mean stuff you see through. There's things they call volcanic glass. That's lava that is cooled so quickly, and you'll usually look at that and see a bright, shiny surface there, and it looks sort of like glass, only it's very, very dark. That's also a glass because it's an amorphous solid. So let's look at the liquids. Now, I think we went through how you go from one to another. I remember that last time. We talked about how you go from one phase to another phase, or one state to another state. But a liquid also has that proximity. The atoms of the molecules stay relatively close to each other. That gives it a definite volume. But they're not in a crystal structure, so therefore they can slide past each other very easily. So that means they have no definite shape. They take the shape of their container. Now, these typically exist at higher temperatures than their respective solids. Of course, you can have some liquids that occur as liquids at very high temperatures, and other things that occur at liquids at very low temperatures, and have solids that would be, so you can mix up. But for a given material, the liquid phase of that material will be at a higher temperature than the solid phase or state. The molecules wander through the liquid in a random fashion, except they don't get out of touch with each other. They still are somewhat attracted to each other. The intermolecular forces are not strong enough to keep them in a fixed position, but they are strong enough to keep them in a close range. Okay? So therefore they do have definite volumes, but not the definite shape. Does that make sense? Okay. Gases, by the way, liquids and gases combined are what we call fluids. A gas has no definite volume and no definite shape because these atoms now are free to move. They don't have very much intermolecular forces at all. They don't hold them close to each other, and they certainly don't hold them in a fixed position. So the molecules are in constant random motion, almost chaotic motion. The molecules exert only weak forces on each other, and the average distance between the molecules is large compared to the size of the molecules. Okay? If there was a molecule, and there is a molecule of air right there, say, its molecular dimension is quite small. You have to go several of those over before you find another one, unless they just happen to be colliding, and if they do, they collide, bounce off each other, and go on their merry way without sticking to each other. Okay? They exert only weak forces on each other. Very weak, kind of like they are sort of gravitational forces. Okay. Any questions on gases? The fourth phase or state of matter, and I think we talked about this last time, didn't we? Plasma. Gas is heated to a very high temperature or energized to a very high energy state. Many of the electrons are freed from the nucleus, and therefore you wind up with a collection of free electrically charged ions. They can be ions that have lost electrons or ions that have gained electrons. Either one, but they're free electrically charged ions. In fact, that's almost redundant. If they weren't electrically charged, they wouldn't be ions. If they're ions, they have to be electrically charged. The long-range electrical and magnetic forces allow interactions within the plasma. Plasmas exist within inside stars, like our sun. Most of the material inside the sun are charged ions at such high temperatures they have ionized and they are plasma. Okay, any questions on that? Now, let's look at the different types of matter, okay? Normal matter, matter like the stuff we see here, the solids, the liquids, the gases. This is only about 5% of the matter of the universe, okay? Back when I was in school, this would not even have been a slide, because I don't think we knew beans about dark matter at that time. Dark matter affects the motion of stars in galaxies. It may be as much as 25% of all of the total matter. Now, I find it interesting they're calling energy matter. Now, we know from Einstein's famous formula, E is equal to mc squared, that they are interchangeable. But this is talking about dark energy. This is low-level energy, not enough energy to produce light, to either radiate or incandesce light, but this energy nevertheless accounts for the acceleration of the expansion of the universe, and maybe as much as 70% of all matter. 70 and 25 would be 95, and 5 would be 100. So what we call normal matter is really not that normal, okay? It's rare, okay, in the universe. Amber, right? Gotta find you now. All right. For all the people who may have come in after the beginning of class, I did return the first 2 tests to everybody who was here. So if you weren't here at the beginning and didn't get your first 2 tests back, be sure you see me at lab time, or before you leave today, I'll give you your first 2 tests back. All right. Any questions about types of matter as opposed to states or phases of matter? These are types of matter. Normal matter, pretty rare. It's what we're used to, but pretty rare. Dark matter that affects the motion of the stars and the galaxies, maybe as much as 25% of total matter. Why do we say maybe? We don't know, okay? We know it's out there. We can tell its effect, but we can't see it. There's not much way to sense it, okay? Dark energy, even harder to detect. We know it's there, okay? And we don't know how it does what it's doing or why it does what it's doing. We just know it does, okay? Maybe as much as 70% of all matter. Let me give you a small example of dark matter, okay? Actually, it's a pretty big example. But when a star ultimately dies, okay, most normal stars, I'll put it that way, like our sun or smaller, maybe even a little larger than our suns, when they finish doing everything they're going to do, they become just chunks of carbon or other stuff in space, just out there. You don't see them because they are not hot, they don't incandesce, they don't radiate. You can't detect them with energy things because they're not got enough heat to produce anything. All you can do is tell they are affecting other things gravitationally. Okay? Now, I don't know if they allow a black hole under this category or not. If they were, I would think it would be larger than 25% of total matter. I think maybe a black hole is considered in the dark energy category, but I'm not even sure how they classify these. Other things that would be dark energy. You know, every time that, dark matter, every time a comet goes by, as it gets closer to the sun, it's melting some of its icy structure. It may actually get close enough to the sun to melt solid structure, and as it does, it leaves trash in its path, dust and particles and stuff like that. And that stuff you can't see. When do we see those particles? It's the only time we usually do. When we pass through that trail of dust and particulate matter, after it's been just left hanging there, and then at nighttime when it goes through the Earth's gravitational field, attracts it, it comes into our atmosphere, heats up, and becomes, especially at night. It does it in the day too, you'll never see it. Meteors, okay? Shooting stars, falling stars. They're not stars. Those are pieces of dust and trash left over from various things, usually meteors, that have come intersected our Earth's orbit around the sun, and then we attract them, they come through the atmosphere. The friction there burns them up, and that's what we see as shooting stars or falling stars. They're not stars, little bits of matter. That would be another example of dark matter. Dark energy, I can't even give you examples of that, except possibly that's what a black hole is. I don't even know if they place that in that category or not, but it's just the energy out there that we can't account for. We can sense it, we can see what it's doing to other things, for instance, accelerating the expansion of the universe. Why? I haven't a clue, because most matter attracts things gravitationally. This is expanding things, so it has to be an energy form, and the exact nature of it beats me. Might be a good paper topic if any of you are interested in that type of thing. Any of these would be. Now we get into 9.2, which is density and pressure. We're going to start with density. Now, let's say that you had a chunk of copper, okay? Say a block of copper. Or you had so much copper wire. Or you had a few of the very old copper pennies, okay? Original pennies were made out of copper. These got cheaper metals in them because that much copper costs more than a penny, okay? In the old days, that was about a penny, so that's why they made them out of copper. Copper's gotten more expensive now, so they mix them with really cheap alloys. Still keep the copper color, but it's not all copper. Well, whether you had a chunk of copper, a wire of copper, or a penny of copper, if you had one, how do you know it's copper? Because there may be several pounds of this, a few ounces of that, just a few milligrams of that, you know. How do you know that it's copper? The density of a substance of uniform composition, like if it's pure copper, pure iron, whatever, is defined as the mass per unit light. Now, the symbol for density is rho. That's not a P, that's a Greek lowercase rho. Rho is defined to be, density is defined to be the mass of an object divided by the volume of it. By the way, that's a capital V, because lowercase v is velocity when you're using it in a parametric sense, and capital V would be, uppercase V would be volume. So the SI unit for density would be kilogram per cubic meter. Now that's a huge ratio, because a cubic meter of something would be approximately a little bit more than that. If you took that, basically that door would be a better example. This doorknob is approximately 1 meter from the floor, and that's approximately 1 meter across, maybe a little bit less than a meter. And if you came out approximately that many things and had a block from that doorknob across and down, that is a cubic meter. I can't think of many materials, especially liquids or solids, if you had a cubic meter on them, you could even move, okay? If you had that cubic meter of water, no way you're going to move, okay, by yourself, okay? Any solid would be one. Gases, yeah, I can handle that, maybe, but not anything else. So the SI unit is really a big unit, a bunch of kilograms in a cubic meter. Often then, we use grams per cubic centimeter. Now that's the old CGS system. That's a lot more doable. A gram is approximately the mass of an aspirin tablet or two, something like that. That would be a gram. A cubic centimeter is basically, if you think of a centimeter being about the width of your little fingernail, so that much high, that much tall, and that much deep, that would be a cubic centimeter. Like one of the little bitty blocks of cubes of sugar that would hardly sweeten anything, that would be a cubic centimeter. That we can deal with. You can handle, you can measure. Kilogram per cubic meter, you can measure it kind of, but you wouldn't even be able to put it on the scale. Okay? Now how are these related? 1 gram per cubic, boy, do they have that backwards. Terribly backwards. 1 kilogram per cubic meter, no, that's right. No. 1 gram per cubic centimeter is the same as 1 kilogram per cubic meter. I mean, 1,000 kilograms per cubic meter. Okay, now if you are a little bit doubtful of that, let me explain how that works. Let's start with, let me get my pen activated here. If you have 1 gram per cubic centimeter, and you're trying to convert this to kilogram per cubic meter, okay? When you're doing conversions, always put the units in their place, okay? Now there's 2 conversions you got to do. Which one you want to do first? Grams to kilograms or cubic centimeters to cubic meters? I don't care. Grams, okay? Let's start with grams and kilograms. And this is, pardon me? Brianna. Okay. I was just trying to find you here. No, I found you. I can't get across the line. There we go. Okay. So we're going to start with grams and kilograms. What unit will you put where? One of them has to go above the line, one below the line. This is the line for numbers. This is the line for units. Always put the units in their place. What goes where? Grams on the bottom, kilograms on top. Now, how many grams does it make to make a kilogram, or how many kilograms to make a gram? Match the number with the units. Second, how many kilograms makes a gram, or how many grams make a kilogram? That's exactly right. 1,000 grams makes 1 kilogram. Okay? So it almost makes you think we got them backwards. Let me, I don't think I've allowed myself enough room, so let me do a little bit of adjustment here. Okay. So we got to get from centimeters and meters. Which unit's going to go where? Again, this line is reserved for the numbers. Always put the units in the place first. So what goes where? Between centimeters and meters. One goes on top, one goes on bottom. Which goes where? Which centimeters at the top? Perfect. Centimeter at the top and meters on the bottom. Now, before we start messing with the cubing, let's get our conversion done. How many centimeters in a meter, or how many meters in a centimeter? What's another name for this copper-looking coin? A penny. How much is it worth? 1 cent. How many of these would it make to make $1? 100. There's your conversion. 100 centimeters makes 1 meter, right? 100 centimeters makes a meter. Like 100 centy dollars or pennies make $1. So this is 100 centimeters makes 1 meter. But we're not dealing with centimeters and meters. We're dealing with cubic centimeters and cubic meters. So that means we got to cube the 10 and cube the 1. Now I can cube the 1. That's 1, okay? But what is 10 cubed? Oh, that was 100. Goodness gracious. 100 cubed. Yuck. Okay. I said it right, I think, but I wrote it wrong. Okay. 100 cubed. What is 100 cubed? Second? A million. You got 2 zeros there. When you cube it, you get 6 zeros. 1, 0, 0, 0, 0, 0, 0. So 1 million cubic centimeters makes 1 cubic meter, because 1 cubed is still just 1. Well, now we can wipe out 3 of these zeros with 3 of those zeros, and sure enough, you get that 1,000 kilograms per cubic meter is equivalent to 1 gram per cubic centimeter. Why is that? A cubic meter is so stinking big. Okay, so it takes 1,000 kilograms to fill 1 cubic meter of something that has a density of 1 gram per cubic centimeter. Does anyone know what has a density of 1 gram per cubic centimeter? What you got in your jug? I hope it's not moonshine. Water. Okay. Water is 1 gram. By definition, that's 1 gram per cubic centimeter. So that would be 1,000 kilograms per cubic meter. So remember that cubic meter I pointed out over here? That's from the floor to the doorknob, about the width of the door, and about out to here. Okay? If that block, that cube, was filled with water, it would have a mass of 1,000 kilograms. Does anyone know what 1,000 kilograms is, approximately? In metric terms first, exactly what would that be? Is 1 megagram. Okay, that's the next unit up. What would that be approximately equivalent to in poundage?
The kilogram is 2.2 pounds.
Okay.
So it would be, what was it, 1,000?
Yeah.
2.2 would be like
2,200 pounds. Okay, that would be more than 2 tons. 2.2 tons of water would be right there. So when you say 1,000 kilograms per cubic meter, you're talking about what they call a metric ton per cubic meter. Yeah, I mean, that's a lot of matter. So that's why we don't usually talk about these units. That's why that one's a lot more convenient to use, because the numbers are so huge in kilograms per cubic meter. Okay. And we have just verified that this indeed was true. Okay? Now, there's a table in your text that lists some of the common materials and their densities. Okay? And these aren't in any special, well, no, they're not in any special order. What is the sort of the standard for density? What material? Water. 1 gram per cubic centimeter, which would would be 1,000 kilograms per cubic meter. And let's see, Allison, is that right? All right, has anyone else come in since the call roll? And for all those who did come in, when we go to lab time or have a break or something like that, be sure you get your first 2 tests from me. The last person to turn in some work finally got the first 3 tests in fact, but I can only return 2 of them to you now. Okay. Oh, now I can return all 3 of them. So all of you can pick up that next one when we take a break. Okay. So I can return your first 3 tests to you. Now that person didn't turn in her labs, so I'll have to wait and see if she's going to turn in her labs. She's not been here to do them, but she can listen to them on YouTube, and see whatever she can on YouTube, and do as much as she can. If she gets them in, then I can return the labs if she gets those 2. But that's, I don't know. So let's look at some of these densities. Water, we said, was 1 gram per cubic centimeter. What's another thing you know on the table that's pretty close to the density of water? Anybody? It's on page 269. Say again? Ice. Now what do you notice about ice? Is density greater or less than water? Less. Okay, now this is actually given in kilograms per cubic meter, which are the is the SI unit. So this is all times 1,000. Okay, so 917 kilogram per cubic meter. Now, water, even though it's the most common compound on the surface of the earth, like 76% of the earth's surface is covered in water. And a lot of times that water is very, 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 very deep, like miles down of water, okay? So the most common material on the surface of the planet is also one of the most unusual materials on the surface of the planet. Number 1, that water that Nick is drinking should really be a gas. Its molecular weight is 18, but it's a liquid. Most gases that you run into have molecular weights several times that of water, and yet water is a liquid. And the reason is that hydrogen bonding that goes on in water. It's an electrostatic type bond that makes it a liquid at normal temperatures and pressure. But another thing that's really amazing about water is it's about the only substance, I think, known to man, naturally occurring substance anyway, that when you go from the liquid state or phase to the solid, most of the time materials shrink when you go from liquid to solid. Water expands. It has the solid water, ice, has a lower density than liquid water. Is that important? Does it matter to anybody?
Yeah.
How? Why?
Because, well, I don't know if that matters, to be honest, but maybe polar,
You're pretty close.
polar ice caps or something like that?
Yeah. That if water, when it froze, when it got cold enough, solidified and the solid was denser than water, then all your lakes, your rivers, your streams, your oceans would freeze from the bottom up. And if that were the case, life would basically be over, because the fishes, everything that lives there, they wouldn't. They could not, because they would be forced to the surface or they freeze to death. But because ice is less dense than water, you have an air pocket. On the polar ice caps, you have an air pocket between the liquid and the solid, because the solid floats. It also makes it more convenient when you have iced tea. The ice floats, not the tea, because then as it melts, the cold water goes to the bottom, and it makes life a lot more pleasant. But actually life wouldn't even exist as we know it if ice didn't float. It's the only substance I know of that whose solid is less dense than this liquid form. Okay, aluminum, 2.7 times the density of water. Iron, 7.86, almost 8 times the density of water. Copper, almost 9 times the density of water. Silver, 10.5 times. Lead, 11.3 times. Gold, almost 20 times the density of water. Platinum, more than 21 times. Uranium, almost 19 times. Glycerin, a material. Where do we find glycerin? Okay. Any of you use antifreeze in your car? One of the materials in antifreeze is, I'm pretty sure, is glycerin. Okay. It's just beyond water. It's 1.26 times 10 to the third kilogram per meter cubed. Alcohol, on the other hand, a little less dense than water, 0.806. Benzene, 0.879. Mercury, 13.6 kilograms times 10 to, or 13,600 kilograms per cubic meter. Now, what is a little strange about mercury, though? Most things that dense are solids, for sure. But mercury is, at normal temperatures and pressure, a liquid. Notice there, 13.6 times 10 to the third kilograms per cubic meter. When someone says something is really heavy, what metal do you think of? Heavy as lead. Lead's density is 11.3 thousand, 11,300 kilograms per cubic centimeter. Mercury, 13.6, meaning that if you had a pool of mercury and put lead in it, the lead would float. It is less dense than mercury, okay? And yet mercury is a liquid. Air, 1.29 kilograms per cubic meter. That cubic meter I showed on the floor over there, illustrated over there, that cubic meter of air is better than 1.25 kilograms. That would be not quite as heavy as this book is. This book is probably closer to 2 kilograms, but it would be about half the book. The total weight of air in that cubic meter of space would be about half the weight of this book, believe it or not. Oxygen, almost 1.43 kilograms per cubic meter. Hydrogen, the lightest of all gases, 8.99 times 10 to the minus 2 kilograms per cubic meter. Helium, a little denser than hydrogen, 1.79 times 10 to the minus 1. So that would be 0.179 kilograms per cubic meter, where hydrogen would be 0.09 approximately. Okay, so those are some of the densities in the table. Most things that are around 1 density, 1 gram per cubic centimeter, 1,000 kilograms per cubic centimeter, anywhere on either side of that are usually, but fairly close to that, are usually liquids, and gases, and water is the only liquid that low of density. Okay. The densities of most liquids and solids vary slightly with changes in temperature and pressure. Of course, when something heats, most of the time it expands, so it gets less dense. If it cools, it contracts and gets more dense, water being the exception to that. So the densities of most liquids and solids vary slightly with changes in temperature and pressure. The density of gases vary greatly with changes in temperature and pressure. when I was living in Lincoln, Nebraska, that's where I did my some of my graduate work. Was up there for 5 winters, and those were really cold winters, by the way. Not for them, but for me it was. And I remember one, I believe it was probably a Sunday afternoon, I went over to this. I was doing some work with a kid that went to our church. His dad left the family, so he didn't have a male role model. I thought, Mom had asked the church if any of the guys would be able to do that. I thought, I'm not married, I don't have kids, I couldn't do it. Turned out that we played on the church softball team, and we got along so well. I said, well, maybe I can do this. So I would go over. And one Saturday night, he had left the basketball out after shooting some, and that Sunday he went to pick it up that afternoon, and he said, oh no, I must have punctured the ball because it's going flat on me. I said, Matt, don't worry about it too much. Take it inside, and we'll shoot some hoops later. He thought I was nuts. He took it inside where it was probably pretty close to 70 degrees Fahrenheit, whereas outside overnight it had probably got below freezing. It usually was, it seemed like there. And when he went in about half hour, 45 minutes later, the basketball was just as tight as it could be. If he'd have pumped up the ball when it was cold, it might have actually ruptured when it warmed up some, because gases vary greatly with changes in temperature and pressure. Okay. There's a dumb little story I'd like to tell, but we may not have time for it, so I'll hold off on that. The higher normal densities of solids and liquids compared to gases imply that the average spacing between the molecules in a gas is about 10 times greater than the spacing between solids and liquids. Between solids and liquids, the distance between molecules, really, really close. And they're about the same, approximately, solids and liquids. But gases, 10 times further apart. Okay. Now, if you notice when I was talking about those densities in the table, I started off saying aluminum was 2.7 times as dense as water, iron almost 8 times, copper almost 9 times. What I was really referring to there was specific gravity. The specific gravity of a substance is the ratio of its density to the density of water. And basically, since the density of water at most common temperatures and pressure, at least in kilograms per cubic meter, is 1 kilogram per cubic meter. So if you were to divide the density of the material by the density of water, well, no matter what units you use, you come out with a dimensionless quantity. So the density of water is 1,000 kilograms per cubic meter. You divide something else with 1,000, so many thousand kilograms, like aluminum, 2.7 or 2,700 kilograms per cubic meter, you would get a specific gravity of 2.7. So specific gravity is a dimensionless quantity because you're dividing kilograms per cubic meter by kilograms per cubic meter, but then you get a unit, a number, that basically is the same as the density of the material in grams per cubic centimeter, because that's based on water being 1. So specific gravity is that ratio of the density of the material to the density of water. A lot easier to mess with because they're smaller, reasonable numbers, and you don't have any units you have to hang around with. All right, before we move to pressure, there is a quick quiz on page 269. This is 9.1. Suppose you have 1 cubic meter of gold. I want to be your friend, okay? You're a really good friend, too. A cubic meter of gold would be 19,300 kilograms, okay? You would be a rich person, a very rich person, if you had 1 cubic meter of gold. And but not just that, you had 2 cubic meters of silver and 6 cubic meters of aluminum. Rank them by mass from smallest to largest. So what you have is 1 cubic meter of gold, that's AU. You have 2 cubic meters, cubic meters. Goodness gracious, I can't believe I did that. Okay. I'm saying cubic meters and writing centimeters. Cubic meters of gold, 2 cubic meters of silver, that's AG, and 6 cubic meters of aluminum. Okay? It says rank them by mass, smallest to largest. How do you do that? Let's think back about what a density is. What is that formula for density? Rho is equal to, second, M over capital V, mass per unit volume. So if you're ranking these by mass, what you have to do is get the mass of gold would equal the density of gold times the volume of gold. Right? Multiply both sides by volume, and you get density times volume is equal to mass. Okay? So we can come up with what the mass of that gold is. From the table, the density of gold is 19.3 times 10 to the third kilogram per meter cubed. Multiply that by the volume of gold, what we just said there, 1 cubic meter. There, I did it again. Cubic meter, okay? Well, the cubic meters cancel out, and that gives you 19.3 kilograms . 19.3 times 10 to the third kilograms of gold. Okay? Again, 19,300 kilograms of gold. How about silver? Well, its mass is its density times volume, which will be the density of silver, 10.5 times 10 to the third, 10.5 times 10 to the third grams per, no, this is kilograms per cubic meter. Okay? But you had the volume of 2 cubic meters, okay, of silver. So when you double that, you get 21 times 10 to the third kilograms, because the cubic meters go out. So guess what? You got more silver than gold, but not by much. The mass, so right now gold is the lesser, and silver is a little bit more. But you had 6 cubic meters of aluminum. What was the density of aluminum? Okay, what's the density of aluminum? From your table, 2.70 kilograms per cubic meter multiplied by 6 cubic meters. Cubic meters go out, and that leaves you with a mass of aluminum of, that would be 42, carry the 4, 12, 16.2 times 10 to the third kilograms of aluminum. So even though you had 6 times as big a volume of aluminum than you did gold, you still have more mass of gold than you did aluminum. By quite a bit, too. More than 3 kilograms. Okay? So from least to greatest, gold, aluminum, silver. Gold, aluminum, silver. And that would be A. 9.1 should be A. Find it in here. Topic 9. Whoa. Either I misread something or they got it wrong. 9.1, they said C. I'm sorry. I said it right the first time, but then said it wrong afterwards. Aluminum, gold, silver. Aluminum, gold, silver. Yeah. Sorry about that. Aluminum, gold, silver, that would be number C. Any questions? Now, that covers density, and then specific gravity is just a dimensionless quantity that resembles density. Okay? What in the world is pressure? Okay? Pressure is force per unit area. Okay? Force per unit area. Now the first thing to note here is the force exerted on a fluid, by a fluid on a submerged object at any point is perpendicular to the surface of the object. Okay? So if you had a cube down there, the force exerted on that cube would be a force in that direction, this direction, this direction, that direction, down, up. Would be on perpendicular to each side of the cube. Okay? The average pressure, P, is the force divided by the area. There is the definition of pressure. Average pressure, P. That is a P, not a rho. Pressure is P, capital P, is force per unit area. And parameter-wise, they make both of those capitals. That's how we define pressure. Okay? Now, the SI unit for pressure is a Pascal, named after a French physicist, mathematician named Blaise Pascal, a very brilliant guy who did a lot in physics and in other areas. He was not it's hard to say. I usually think of him as a bit more of a physicist than a mathematician, but then too, when I think another way, I think, no, he's more mathematician than physicist. He covered it all pretty well. Any of you ever heard of Pascal's triangle? Yeah, Blaise Pascal. Pascal did a lot of work in statistics back before it was even a field. He and Descartes, maybe one or two others, were really in many senses, the parents of statistics. Now, this unit of Pascal is an incredibly small unit because the Newton is not that big anyway. But now remember what a square meter is? That's basically the area of a door beneath its knob, okay? All the way across and down. That's a huge area divided by a fairly small unit, Newton. So typically Pascals are very, very small quantities. In fact, if someone were to come in, open the door, they would decrease the pressure in the room by a few pascals. Would you notice that? Probably not. Okay? If they close the door reasonably, unless you had a finger in it or something, you probably wouldn't notice any difference at all, because a few pascals hardly noticeable. So when we're filling our tires with air, What unit do we use? Pounds per square inch, often called PSI, and that's a fairly reasonable number, okay? When they do the conversion to the SI unit, Pascal, they don't even mess with Pascal. So they go straight to 1,000 Pascal. What would that be called? Well, prefix means 1,000. Kilo. That would be a kilopascal. And look on your tires. They'll say so many kPa and then in parentheses PSI. Okay, those are not the same numbers, but fairly similar quantities. Now, does anyone know what normal atmospheric pressure is in PSI? Anyone?
Is it like 6 something?
14.7. Close to 15. 14.7 PSI. Pounds per square inch. Force in pounds, square inches. Now, what is a square inch? It's almost your two thumb joints there. Side by side, that's approximately a square inch. Now think how many square inches we've got covering our bodies. That's a lot. A huge number of square inches. And for every square inch, there's 14.7, almost 15 pounds of force on our bodies. That's a lot of weight. Why don't we get crushed? Why don't we find it hard to move? Because we have probably 15 pounds per square inch pushing out of our body, okay? We don't get crushed because our bodies are pushing out with about the same as being pushed in. Now, what would that be in pascals? You wouldn't even measure it in pascals. You would measure it in kilopascals, thousands of pascals to match that 14.7 PSI. Okay. The force exerted by a fluid on a submerged object at any point is perpendicular to the surface and increases with depth because the further down you go, the more weight of fluid you have above you, so the greater the pressure. Okay? Okay. Now, we also sort of mentioned a little bit before. Yeah, all objects are deformable. I would say compressible. Deformable is true too, but basically, unless I'm off what they're talking about, they are deformable too. But I would say compressible is a better word for it. It is possible to change the size or shape or both of an object through the application of external forces. Now, yeah, I think I know what they're talking about now, okay? When the forces are removed, the object does tend to return to its original shape. If it does, that object is undergoing a deformation of that type exhibits elastic behavior. Now, didn't we talk about this sort of briefly about hitting balls with things? Did I mention that? I've got one physical science class, 2 physics classes, and 3 math classes. I can't remember what I've talked about in each one. But did we talk about that? Have you ever seen a slow motion shot of a tennis racket hitting a tennis ball?
Oh yeah, how it flattens out.
Yes, it does. The ball deforms, flattens out, and actually the tennis racket bulges out in the bat. Okay? But then when you complete your swing and the ball leaves the racket, the ball returns to its shape and the racket returns to its shape. Same thing is true about a golf club on a golf ball. Believe it or not, that golf ball does flatten when the club hits it. And the club, you might even sense bends a little backwards, okay? And then when you follow through on it, the ball returns to its shape, the club returns to its original. Same thing with the bat and the ball, okay? If you were to study it and look at it, you would see that hard old baseball basically almost the bat indents that baseball ever so slightly. And then when you complete your swing, the baseball returns to its shape. And the bat, you don't notice it, but it does flatten a little to where it was. The wood or metal does get a little closer together and then come back. Have I given y'all the volleyball example? I don't recall that I have. Have any of you played volleyball? Okay. And a volleyball, when it pumped to the regulation thing, is not a soft ball. I mean, it's softer than a baseball, but it's still it's about equivalent to footballs and basketballs, right? As far as the pressure is. Okay, so those are not soft, you know, softer than baseballs, yeah, and golf balls, but they're still not very soft, okay? Most of my college time, I usually tried to play intramural sports just because I figured I needed the exercise. I tend to put on weight too quickly and rapidly and hard to get it off. And I like to do things, okay? And I wasn't very good at volleyball, but I enjoyed playing it a lot. And when I was on my, I guess it was in Nebraska, yeah, we were in a co-ed volleyball league. And we had a couple gals that were on our team. One was really tall, she was pretty good. And one was a great setter. She was a lot shorter, but she could really set it. They had played together in high school, which was fortunate for us too. And the guys were okay too, but they were pretty good. But we went out to play against this one team. They had this gal that was taller than our gal. I mean, ours was close to 6 feet. Theirs was about 6'2". And she had definitely played some high-level volleyball. I'm guessing collegiate level, and she may have been on the Masters. And she had a little setter that could set her up perfectly too. Boy, when she went up, that ball came down hard. I mean, she could time it perfectly. So, you know, in volleyball, how you rotate around. So at some point, you're basically going to be against everybody else. Time came for me to be right across the net from her. She was right where she wanted to be because that was right where she liked to assume she was right-handed. It was just perfect for her. So I knew it was coming as soon as we served and it went over there, and her little setter set her up perfectly. So I went up to make as big a surface area as I could in case I knew the ball was coming, and it was going to come hard. I was hoping to get up there and block it with something and it go back across the net. Unfortunately, she had a good downward trajectory on it, and it hit me square in the face. It was a hard volleyball. Literally, I felt it touch both ears simultaneously. My face deformed that volleyball pretty drastically. All I could see was Wilson, you know, but yeah, that was beside the point. It also did a little bit of deformation of my face, and but then it bounced back, unfortunately, on my side of the net. So didn't quite do like I wanted it to, but it was everything like that type of deformation, when it goes back to its original shape, we call that elastic behavior. Now let's see. Whoops, I really talked a little over, didn't I? Let's see what the next slide is. Elastic properties. Goodness, I don't even see this in here. I have a feeling they have rearranged the book just a little bit here. I don't see stress and strain. I know what they are, but I don't see them here. All right, here we go. Wow. What we've been talking about here at 9.3 on the slide set really is 9.10 in here. So what we're going to do, we'll come back to this later. I want to follow the book more. We'll come back to these moduli. Like I said, this is the first time I've taught from this new edition, so I wasn't aware that it was doing this. Wow. Oh man, there's quite a bit of change here from what we've had before. There is pressure. There's a figure on page 269. Then it gets into deformation. And where do we get into variation of pressure with depth? There we go. Okay. What's 9.3 in our text is 9.4 on the slides. So we'll pick up and start with this next time. We did pretty much do the pressure like we should have, but I got off into deformation and didn't realize the book wasn't in the same place. So we'll pick up and go from there next time. So I'm going to pause. All right, I've just passed out the lab for those people who are here, and one or two that weren't. The first page of the lab, now this was the last topic 6, momentum. That's what the lab is on today. The first page of the lab is just short answer questions based on topic 6. So you'll need to get the answers from this in the from your text, okay? From your notes, from PowerPoint, from wherever you want to get those, okay? And y'all can work together, so do that. The experiments dealing with it, which is the second page, we're going to do, I think we're going to do down in 259. So the reason I'm saying this now is I've got to go scout out and see what room's available. And if I find the room available, when I find it, I'll come back and tell you, and we'll go down and do the experiments. But you don't need to be wasting time. You can actually be doing it now. Now, I do know that Courtney came in, and I didn't mark you present, I don't think. There you are. Did anyone else come in since I was yakking my mouth? Okay. I got everybody who was here. Okay. Well, then, y'all start working on the questions, first page of the lab, and while you're doing that, I will go down and see what room we're going to be going to. Good deal, thank you. Got another paper in, way to go, okay? And by the way, for those who haven't yet, remember you only got a couple more weeks. So that may only be one more weekend, maybe two, I don't know, that you can work on those if you take advantage of weekends like that. So if you'll continue, get started on the lab, I will go down and see if I can find a room for us. I'll come back and let you know where we'll be. disconnect a few things here. You can continue working if you'd like here until I go down, or you can head down there ahead. If you want to take a quick break, you can do that as well. I've got to get disconnected here though first. Yes, it did. You didn't get one.
Thank you.
So which letter is it?
259. Down the PHY stairs. Okay, we've started weighing the mass of the balls, and what did you say?
This one's 70.
70 what? 70 is just a number.
70
Grams, okay? But I want you to record that in kilograms. So what would be 70 grams?
0.7 grams. No, 0.07 grams.
0.070 grams, okay? So you can take that ball off and place it somewhere else, okay? Now, someone else come and do one of the others. I'll get as much participation as possible here. So he did the one farthest over here, do any one of the other three. Okay? It's zero, always zero first, because you may be looking at it differently from what he was. Okay? What you got? 70 grams, which is how many kilograms? 0.070 kilograms. So put that over there to the right of that last one. Okay, 2 more balls to go. Anybody? Anybody? Yeah, I got it here. Good. Come on, need 2 more people. The longer it takes. No, you've already done it. The longer it takes, the longer we'll be here. I'll be here till 9 o'clock tonight, so if y'all want to. Never mind, you didn't want to. Either the small one or the big one, okay? 0 first. Okay, 70 grams, which is 0.070 kilograms. Okay, small ball. Who wants to do the mass of the small ball? Don't be shy. As long as you like, I've got all night. I like having y'all here. One more to take the mass. That's all it is, folks. Anyone go do it? No, you've already done it. All right, good deal. Little bitty silver. 0 to scale. Second. 25 grams? Okay, which is? That's how much? 0.025 kilograms. Very good. All right. Now, all 3 of these big balls are at 0.7, you said, so 0.070. So I'm going to put one of those on the track and take the second one. And I don't know what 1 meter per second is, but I'm going to give it a good scoot down the track. I might need someone over here to be a ball catcher for me because I don't want to wreck this other equipment. So if someone would do that, I'd appreciate it. Okay, good, thank you. Just come over here because that's where it's going to be coming. And I'm going to try to approximate 1 meter per second. So what I want you to do, and all of you need to be looking because this is what you're going to fill in the lab. You need to define what happened. Now you can name originally the moving ball is ball 1 and the stationary ball 2, or that ball 1, this ball 2. Whatever you do, just be consistent with it. So I'm going to roll this ball toward that ball about 1 meter per second. Now what I want you to do is focus on what happens right after the collision, immediately after the collision. Something else may pick up later, and there's a reason for that. What are we studying this lab on? What's the title? Momentum. There are 2 types of momentum. Does anyone remember what kind they are? We only studied one of them, but there is a second type. What's that? Okay, most momentum is conserved with isolated systems. The 2 types. What we're trying to study is linear momentum. That's the symbol P. And what we didn't talk about was, I mentioned it, but just in passing, angular momentum. Because this ball is not going to scoot down the thing, it's actually going to be turning, it will have a little bit of angular momentum too. So after the initial collision, then when that happens, that's what I want you to describe. After that, you'll see this ball do something a little else, and we'll talk about that later. So you ready to watch? Now I've got to get in front of you, but I'm going to try to get down and out of sight. Can you see the scale? See the track. Everybody? Are you looking? Okay, you ready to catch? I'm going to try to go about 1 meter per second. Okay, how would you describe the motion of those 2 balls? What happened? What happened? Second? Okay, the whichever you call ball 2, you can do that. Describe the motion of the two balls, ball 1 and ball 2. Now, whichever one, I don't know which one you named ball 1, what was the initial momentum of ball 1? Say again? Was ball 1 your moving ball or your stationary ball? I don't care. The moving? It doesn't matter. If it's a moving ball, say again?
I just said moving ball.
I couldn't hear.
I was just saying the moving ball.
Okay, the moving ball. What was the initial momentum of that moving ball? Whichever one you named it, ball 1 or ball 2, what was the initial momentum of the moving ball? A little louder. How do we define momentum? Linear momentum. Second. MV, mass times velocity. What was the mass of ball 1? 0.070 kilograms, and the velocity approximately 1 meter per second. So what was this momentum? A little louder. 0.070, but what units? Second. Kilogram meter per second. The same units as mass times velocity. Kilogram meter per second. What was the initial momentum of the stationary ball? 0. Okay. Now, what would you have said the initial momentum of the system was? This is answer D. It would be the sum of those two. Something plus 0 is that something. So it would be whatever the momentum, initial momentum of ball 1, or initial moving ball. I'll put it that way. Okay. Does it appear that momentum was conserved? The momentum of the system before the collision equal the momentum of the system? Yes, it does appear that way. Because afterwards, the moving ball was now stopped, and the stop ball was now moving with about the same speed. They had the same masses, so momentum did appear to be conserved. That was E. Now, this time I'm placing 2 large balls on the track near the center. Okay? I'm going to roll 1 ball toward the 2 balls. Okay? Now, do any of you want to predict what's going to happen? Okay. It is time for me to call roll, so hold just a minute. Sorry. If A still isn't here, Nick kind of is here. Kiara's still here. Courtney Brooks still here. Raven just came in. Shakina is still here. Charity Hopkins hasn't made it in today. Courtney Humes is still here. Essence is still here. Off one. Oh, Embry's still here. Embry's still here. Ryan hasn't made it in today yet. Monique hasn't. Oh, there you are. Did you just come in when? Okay, I didn't catch you. No, I'm sorry. I did catch you. Larius isn't here. I was on the wrong one. I thought I called you when you came in. Monique is still here. Sasha is still here. Allison is still here. No, I saw you somewhere. Where are you? There you are. Okay. Okay. Darius has not made it yet. Scarlett is still here, right? Yeah, I see you. Okay. Will is still here. He's somewhere back there. Yeah, he actually did some of the measurement. Brianna is still here. There you are. I see you. Naya is still here. I got it. And Rhea just came in. And Dakota is still here. There you are. I see you. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 2, 4, 6, 8, 10, 12, 14, 16, 17. Now, for those who just got here, or got here recently since we started, the first page here are general questions that you get from the reading of the chapter, that are topic 6. Okay, so you have to go back there, the lecture, the PowerPoints, wherever you want to get those. And you can work together. I encourage you to work together. So the first page is that. The second page, those who just came in will need to get the data for 1A. We measured the mass of the 4 balls. We've already done 1B. We've done 1C, 1D, 1E, and we're just set up to do 1F. 2 balls are on the track, and 1 ball I'm going to roll toward those 2. Did I hear someone make a prediction of what's going to happen?
Yeah, the ball farthest away, the ball at first of that is going to move. But the ball that gets hit first is not going to.
Okay, we'll see if Nick's prediction works. Someone want to be my ball catcher?
I'll do it.
Okay. Oh, she's right here. Okay. So I'm going to try to do, can everybody see? I'm in the way, I know. Are you looking? Now again, you're paying attention to what happens right at collision. Not what happens later, but right at collision. You ready? Here goes. Sure enough, pretty close to what Nick said. Okay? All right. Everybody got it? Now you identify which one's ball 1, 2, and 3, and describe what happened. Do you think momentum was conserved there? Yes, because the first ball was the only one with momentum initially. The other 2 had 0 momentum, but after the collision, the third ball took off, or the last ball this way took off, at about the same speed the first one had coming in. So sure enough, they had the same mass. So it did appear to be conserved. Now, this time I'm going to roll 2 large balls, one towards the other. Okay, I don't need a catcher on this one. Y'all watching? Now, initially, this one's going to be going this way, this one's that way. What do you reckon the initial momentum of the system is going to be? Say again? If I do this at 1 meter per second to the left, this one at 1 meter, to the right, this one 1 meter per second to the left.
0.
Huh?
0.
0. Why?
Because they cancel out each other.
Why?
They move in opposite directions.
Okay, because momentum is a vector quantity. Direction does matter. Okay? So you see what happens right after the collision. Oh, you got to fly. Okay, I thought I didn't need a ball catcher. Okay. That one was not one to observe. Okay? Let's try it again. Everybody ready? Oh. Why are they losing the track this time? All right, what would you say? Describe the motion.
They bounce back.
Okay, they each bounce back at?
The original speed.
Yes, and it really didn't matter whether it was original speed or not. They could have actually both slowed with the momentum still being conserved. Because as long as they're going at the same speed in opposite direction, this momentum of the system is still 0. Even though each ball had the momentum that was not 0, the system was. So do you think momentum was conserved? Yes. Okay. The next. Okay. Place 1 large ball on the track, roll the small ball toward the large ball. close attention to it, notice I put the large ball just to the left of the center support there. The reason is the large balls roll over that with no problem. The small ball, see, it hits it. So that's why I make sure I get it on that side. Now I'm going to try to roll this one with about meter per second toward the large ball. What do you think is going to happen? Anyone want to make a prediction? Anyone want to make a prediction? So again? Can't hear.
What happens again?
Okay, I'm rolling the small ball toward the large ball. Large ball's at rest, small ball's moving.
The small ball's going to move back a little bit, but the other ball's going to move forward a little bit.
Okay. He said the small ball is going to recoil in the opposite direction. He said a little bit. This is going, the large ball is going to come in the original direction a little bit. I assume you mean slower by a little bit.
Yeah.
Okay. Let's see if what Nick suggested is true. All ready? Okay, here goes. Now, actually, pretty close to what he said. Do you think momentum was conserved there?
Yes.
Why? What was the initial momentum?
There's no energy loss.
It was the small ball times 1 meter per second. That wasn't as much momentum as we've had in any of the others, right? Except the last one, which was 0 total. So that one had a little bit. When it collided, when it reversed and went that way, it now has a negative momentum compared to what it did have. It's raining. Oh yes, it rains every day, doesn't it? Okay. But the large ball did gain some momentum here. The small ball had a large change of momentum, or a certain change of momentum. It's part of its momentum went here, and part of it recoiled that way in the negative direction. So this one actually wound up with more momentum than that, even though the speeds were about the same. Okay. So again, I think it was conserved. Okay, this time we're going to place the small ball on the track at rest and roll the large ball toward it. So this time I get on the other side of the support and roll it. What do you think is going to happen now? Someone make a guess. This is 1I. What do you reckon is going to happen? Anybody? Make a guess. Going to roll in this direction? Okay, how about the large ball? What's it going to do? You think it's going to continue this way too? Or we'll go back? Or stop? Or fly off it? No, I'm sorry. I won't do that. What you reckon? Keep going in this way a little bit. Let's see what happens. Now y'all describe. Okay? Can everybody see? Okay, you need to describe what you think happened. Ready? Okay, I might need a catcher over here. Okay. All right. Okay. Okay. Now again, focus on right after the collision. Right after the collision. Okay, not what happens later, but right after the collision. Everybody see? Oh man. Well, did it come? Okay, that went too fast. Okay, go again. Oh. Yeah, okay. What happens with small ball, large ball? Which? Okay. All right. For those that it was happening pretty quickly, I know it got really dark. Okay? So let's talk about what happened. Which hit your hand first? Huh? Small ball. By a little bit. So the small ball picked up a lot of momentum of the big ball, but not all of it. It went faster than the big ball had been going, but the big ball slowed somewhat because overall the momentum was still in this direction. This had so much to begin with, it gave some to the small ball, it kept some itself. Okay? Do you think momentum was conserved? Yay or nay? Okay. Turn to the back side of that second page. I'm going to do what I didn't have room to put on here. Earlier, we did one ball hitting one ball, and then one ball hitting two balls. This time I'm going to try to do, and this is a little bit harder to do, I'm going to roll two balls toward the one. Does anyone want to make a prediction of what's going to happen there?
If you roll two balls, do what?
I'm going to roll two balls toward the one stationary.
That was just going to gain a lot of momentum.
What's that?
They're just going to keep going.
I couldn't hear.
I mean, they're going to slow down a little bit, but they're just going to keep going.
What? All three or what?
Well, the front one's going to gain a lot of momentum. The back, the two that are hitting it, it's just going to like, they're going to slow down a little bit, but they're going to keep going.
Okay.
You're going to lose a little momentum, but not a lot.
Okay. Those two are going to slow some but not stop. What's going to happen to this one?
It's going to go forward a decent amount.
With the other two or faster or what?
Probably faster.
Okay. All right. I need a catcher. Okay. Can y'all see? I know it's dark. Can you see? Two toward one. Basically what happened? Yeah, two took off and one basically stayed still. Initially it stopped, but then because of its angular momentum, it picked up and got one a little bit.
So you said two balls took off.
Two balls took off and one stayed still. Do you think momentum was conserved? Yeah, because the two were coming in, one stopped. When it left, two were rolling out, one stopped. So sure enough it was. Okay, is the other room lighter than this room? What's that? I know, but the other room might have more sunlight coming in. If it will help your eyes, I would say let's go back to the other room, and you can continue working on the lab, or you can take it home with you, whichever. All right. Any questions about the lab before I shut this down? Okay, how about the first page of questions? Any questions on that? Because once you leave, I won't be here to ask questions. I can't clarify anything on that. You want to go back upstairs? It's up to you. That's right.
I needed to get test 6.
Test 6. Anyone else need test 6? I think they're going to come up in the classroom, so I'll have to go up and get them there. Okay, thank you. Okay, it's just going to take me a few minutes to put things away.
I get test 6.
That's the lab. Test 6? Okay, it's up in the classroom. I don't have it down here. I didn't bring everything down. And anyone who did not pick up the first 2 tests, actually I'll say now the first 3 tests, I can give those back to you when we get back to the classroom.
Here's this test 6.
Okay, great. Thank you. between classes, I'm going to try to figure out if they have any projection on when the power is going to come back on. If it's not, it's going to be hard holding class tonight. We got some daylight here, but what's that?
Can we even start Screencast-O-Matic without the power?
Yeah, it's my computer's still running.
Also, you have Wi-Fi.
Yeah, I don't know if it's loading on Wi-Fi.